I'm going to talk about a big data. It's really more of a ginormous or humongous data problem, which is the data that gets created from satellites that are orbiting around the planet, and how we deal with that. So I'm going to go back in time, talk briefly about how we got there. Global transparency started a long, long time ago, actually probably close to the time that I was born, with the very first satellite systems that were used during the Cold War to be able to act on the basis of facts instead of on the basis of fears. That data was available only to a few people and a few governments, super secret stuff. The covers started to come off in the mid-1980s with the availability of imagery from systems like the French spot satellites that were used to shine a light on the Chernobyl disaster. Really one of the first times that the global population was able to see events happening halfway around the world in places they couldn't otherwise go. Now, the modern industry got its start back in 1992. There were a number of factors that came together. One of them was satellite technology that came out of initiatives like the Strategic Defense Initiative that drove the cost of building satellites to the point where individuals or companies could consider building them instead of having governments build them. The second was Moore's Law, which has always been our friend, that made it possible for your computer, your workstation, or even your PC to actually look at images, whereas previously they were glass teletypes. The end of the Cold War really changed the geopolitical landscape from a relatively static bipolar world to one where there were a lot of open questions, and that led to some changes in the regulatory environment that opened up the possibility of commercial remote sensing. And then the last factor was I had time on my hands because I broke my foot playing paintball 2 weeks before I got married. Bad decision on my part. And I had time to write a business plan. And that was the business plan that led to the creation of DigitalGlobe. Now today, how many people have a mobile device? Like, how many people have looked at satellite imagery on your mobile device? Right? So it's pretty much everywhere. There are probably well over 1 billion people who use mobile devices or web portals to look at satellite imagery. And we're seeing imagery from other kinds of devices like drones being used to support agriculture. We're seeing it used in city planning. And it's becoming effectively ubiquitous. So the thing I want you to think about here is just how big this planet is. So look around the room, you see, there's a bunch of people, there are a bunch of chairs, there are a bunch of tables. Now imagine all the things that are of that size or scale that you can see just in the area of this conference venue, Tysons Corner. And now start zooming out and realizing that it's those chair-sized things, but it's on a planetary scale. That's a huge crap ton of data. And let me just give you a feeling for how much data we're talking about. So if you've heard the analogy, 1 byte of data is like a grain of rice. So DigitalGlobe has, since 1999, collected about 100 petabytes worth of imagery. So maybe 1 container ship full of rice. How about 200,000 container ships, which is enough to go around the world more than once. It's about 40 times the total world fleet of container ships. That is a crap ton of data. Now, DigitalGlobe is operating at a scale where we massively envelope all the other imaging satellites that are out there. In one day, we're doing somewhere on the order of about 80 terabytes a day. And you look at the rest of the industry, by the way, the gray bars are systems that people say they're going to build but haven't actually raised funding for. We represent really the high bar in terms of remote sensing data in the commercial industry. So we like to think of it as data boulders from space that are falling from the sky and crushing any IT department. Where are you going to put 100 petabytes? We captured those in our data center, but basically they were sitting in jail because in order for you to do anything with it, you actually had to have the capacity to work on data with that volume. So I want to talk to you about how we engineered the jailbreak. The first step was elastic cloud computing, which we've heard a number of people talk about here at the conference, Amazon Web Services. So that creates the next problem. How do you get 100 petabytes into the cloud? Well, you could use a network connection. And if it's your home network connection, it'd take you about 300 years. Loading. Even on Direct Connect, which is a much higher speed backbone, it would take you probably 18 months to move the data. Now, Amazon introduced something that was pretty revolutionary. It was effectively a network transport via FedEx or UPS. It was called the Snowball, and it would carry about 70 terabytes worth of data. But it'd still take you about 1,400 of those, so it'd take you a long time. So we need a bigger boat. Or a bigger snowball in this case, which is one that you can see from space. It's called the Snowmobile. And if you see, that's Digital Globe headquarters, and we're going to go zoom in, and you see that little container in the upper left-hand corner, that thing that looks like a shipping container that we're zooming in on. This is all Digital Globe satellite imagery, by the way. That's a Snowmobile. It's 100 petabytes worth of data sitting in the back of a shipping container. And it's actually the fastest network transport device on the planet. It just takes you a while to load it up. But once it gets going, it goes really fast. The second technique was deep learning. We've talked some about that at this conference. And deep learning, I don't really think of it as artificial intelligence. It's actually not very intelligent. It's just very good at recognizing patterns. So you can train artificial neural nets to recognize patterns that enable it to operate at scale in a way that you'd never be able to afford enough people to look at scale. So it can recognize those patterns, like, for example, ships. This is the output of an artificial neural net is really good at recognizing ships. The third trend is equally important. So you've got elastic cloud computing that lets you deal with the massive quantities of data and scale out to be able to process them. You've got machine learning, which are the algorithms that let you recognize what's in the image to convert what's basically some of the world's largest unstructured data into something that you can analyze. But the problem is those machine learning algorithms have to be trained. They're fundamentally useless unless you actually train them to recognize a particular type of object. And one of the ways we do that is using crowdsourcing. And we do that actually in two ways. One of them is to train them on the front end, and the other is to QA the output on the back end, because sometimes the machines make mistakes. And it's very useful to have a crowd of humans that have cognitive ability to take a look at the output of the machine and identify where things need to be corrected. And we heard an example of that earlier, talking about the Tesla control system, where a driver in a Tesla is always providing additional input back to the machine to make the machine get better. Now, we operate the largest crowd in the world for training. How many people remember MH370, the Malaysian airliner that went down, where there was a massive search? And there were about 8 million people around the world who were looking for debris, signs of debris. That was using our crowdsourcing platform. So we've had north of 9 million people engaged. TomNut is the platform we use. And we've collectively analyzed about 1.2 billion square kilometers worth of imagery, which is about 10 times the land surface area of the planet. So we've had people looking at a lot of imagery, and that's fed into training about 500,000 different training images for various machine algorithms. So I've been talking a lot about scale and bits and bytes. I want to talk to you about how you actually use this data. GBDX, by the way, is DigitalGlobe's cloud platform for analyzing data at very large scale. Let me give you one example of a use case. So imagine you want to know for, say, a house. How tall is the house? Is it a 2-story or a 1-story house? Is the roof a peaked roof or a flat roof? Are there trees nearby? Is there a solar panel on the roof? Is there a swimming pool nearby? Maybe 60 parameters around the house for an insurance company. So you could send somebody out and go take a look, or you could call the homeowner up and ask the homeowner. Well, one of them is expensive and the other one may not be the most accurate. And let's say you want to do that over a territory the size of Australia with about 15 million structures. Well, that's where something like GBDX comes into play, because it can do that with the scale of machines and the speed of machines at a price point that is vastly less than trying to do it with humans and clipboards, and with an accuracy that's greater than relying on volunteered information. Among other things, we leverage satellites to do things that you wouldn't necessarily guess they could do, like, for example, tell you what the roofs are made out of. Well, with the naked eye, it's pretty hard to tell, but with shortwave infrared, which we carry on one of our satellites, we can actually tell the type of material that a roof is made out of. So we're able to collect data at a massive scale and convert it into a usable form, in this case for an insurance application, but you can imagine that that same data set can drive a variety of other applications, like say a solar panel installer, and you want to identify candidates for installing solar panels. Or Facebook. One of the things Facebook was interested in was figuring out where people live so that they could deliver internet to people who were previously unconnected, and they've used GBDX to identify where populations are in the developing world. Another example is monitoring pipelines. There's about 2.5 million miles of pipelines, energy delivery pipelines, just in the United States alone. And monitoring a piece of infrastructure like that by sending people around isn't very cost effective. And yet you'd kind of like to know if things are happening near either an above ground or a buried pipeline, like people building things that you didn't know about. You can run a query against a digital globe or satellite imagery data set using GBDX and answer questions like, has there been a change in vegetation? Has there been a change in construction nearby? And the mechanism that we enable that by, one of many actually, something we call Answer Factory that lets you identify a query, like I want to count airplanes at airports and monitor trending over time. We also, I heard there was a discussion earlier about the use of Jupyter Notebooks. So we also tie in with Jupyter Notebooks to enable data analysts to do those sorts of queries. Just another example of airports. By the way, one of the things that sort of get your head around, machine learning, it's not perfect. It's not going to give you a 100% accurate answer. And so the sorts of applications where it's really best for are finding, counting, and measuring things. If I want to know, is there a car in my driveway or not, machine learning is probably not the way I want to go. I'm just going to go out and look at the car in my driveway. But if I want to have a pretty good estimate that's pretty statistically accurate of how many cars there are in driveways in the greater Washington area, that's where machine learning starts to really shine. It can deal with really large data sets and give you a level of timeliness and accuracy that's hard to get any other way. This is an example of finding oil tanks. Floating top oil storage tanks is a way of measuring world oil storage to feed into economic models. Now, we're supporting a large and growing ecosystem of both producers of geospatial information, people who create algorithms, for example, for finding ships, and consumers of information. You probably recognize some of the companies that are up there. Now, I want to close by talking about an application that may be actually a little bit more emotional than finding floating top oil storage tanks. I think many of you may be aware of IUU fishing, illegal fishing. And it's a relatively complex issue. It involves basically too many fishermen chasing too few fish. It's driven by economic insecurity. What's the consequence? Well, one of them is less fish. And that's sad. I like eating fish. But there's actually a human consequence to this as well. And I want to talk to you about a specific example of where satellite imagery was used to address that human consequence. But now imagine scaling that using everything that I've talked about to being able to address this problem on a global scale. There are about 30 million people in the world who are still enslaved. And we worked with a group of reporters from the Associated Press over about a year ago as part of an investigation into slave fishing, where young men would be induced with a promise of employment to go work on fishing boats. And they thought they'd make money for their families. But in fact, what they were put into captivity in horrible conditions, kept sometimes for decades, kept on the boats or kept in cages when they were on land. And the reporters with the Associated Press, Martha Mendoza in particular, came to us and said, we'd like to find some smoking gun to help unroll the slave fishing operation. And they said, well, we think there might be slave fishing boats meeting with a refrigerated fish cargo ship somewhere in the ocean. We sort of have an idea of where it might be, but we don't know exactly, and can you help us find them? And so we started to look. And in fact, we found in the middle of the ocean a smoking gun that was these two uniquely identifiable fishing boats that were known to be slave fishing boats because the reporters had actually spoken to escaped slaves who recognized these boats, and a uniquely identifiable commercial fishing boat in the middle. And that was a smoking gun that we were able to provide to the Indonesian authorities, or the Associated Press provided to the Indonesian authorities, that led to the arrest of the captains and the release of over 2,000 slaves and reuniting them with their families. And that led to the award to the Associated Press of the Pulitzer Prize for Public Service. And that's just an example of how all this technology that I've talked about can help all of us see a better world. So with that, thank you very much.